So you are looking at the formulation, and we are happy now with the formulation. It's very important for us to understand that the drugs require to be enteric coated because the activation involves the combination of the reaction, or the activation involves their protonation. So if they are not enteric coated, then they will be protonated very far from their active site, and that will bring us a lot of challenges. Then we look at the SAR, and the SAR is just as we have done, but I just want to now look at the individual drugs, look at the substituents within every molecule, and just mention what the substituents are doing. Already, when we look at omeprazole, we are saying omeprazole has 2 methyl groups and a methoxy group at the center. Methoxy groups, methyl groups are electron donors. That one we already know. Being electron donors, because the oxygen, although it will pull electrons through negative inductive effect, it will add electrons through resonance, and resonance predominates. And therefore, the methoxy group will add electrons into the system. The methyl groups will add electrons into the system, make the nitrogen more nucleophilic, and therefore increase its ability to attack the electrophilic one, increase its ability to be protonated the minute it hits the nucleophile, and then 2, also increase the nucleophilicity of the non-protonated pyridine, and therefore its ability to attack the electrophilic carbon. So that's all we are saying. The methoxy group at position 4 of the pyridine donates electrons through resonance. The pyridine nitrogen resulting in increasing the percentage of cationic pyridine. I think all that we have mentioned. To increase the concentration of increase the percentage of the cationic pyridine, which sequesters the drug at the site of action, increase the nucleophilic character of any molecules of the PPI with an ionized pyridine nitrogen. Therefore, increase the nitrogen, increase its reactivity in terms of attacking the electrophilic carbon. This, in turn, facilitates the intramolecular nucleophilic attack at carbon 2' of the benzimidazole ring, leading to the formation of the active sulfenic and sulfonamide acid forms. The methyl groups at position 3 and 5 also enhance the nucleophilic character of the ionized pyridine nitrogen through positive induction through a sigma bond. So the methyl groups is positive induction. The methoxy group are through resonance. They have negative inductive effect because oxygen has a higher electronegativity than carbon. So they will have negative inductive effect, but because oxygen has 2 lone pairs of electrons, it will push those electrons through resonance into the pyridine ring, and therefore increase its nucleophilicity, and also so increase its nucleophilicity. And once it increases its nucleophilicity, it will increase its ability to attack. It will also increase its ability to be protonated. Carbon 2' position of the benzimidazole is made more electrophilic by the pi electron donating effect of the benzimidazole. Remember, this 5' methoxy group, again in both esomeprazole and omeprazole, again it pushes electrons into the system. That increases the nucleophilicity of the benzimidazole nitrogen, which is nitrogen 3, as we have already discussed, which enhances the N3 protonation, that in turn pulls electrons from the carbon 2'. Remember, that's prime through sigma bonds. This again we have explained. The 5' methoxy group does not exert a negative inductive effect, but the overall does exert a negative inductive effect, but the overall is, of course, through again resonance. So it has a negative inductive effect, but will increase electrons through resonance. The rate of formation of this active and charged pyridine and charged benzimidazole forms is directly correlated with the onset of relief from the symptoms. In fact, obviously, the faster the activation, the faster the relief of the symptoms. Most of the newer PPIs on the market, including esomeprazole, have a faster onset of anti-secretory reaction than omeprazole. But as we will mention that, but we say it is just because of the metabolism. It is not because of anything else. The structure is the same. The reason for their fast activity is the metabolism. The major inactivation metabolics, we looked at metabolism of omeprazole and esomeprazole. Remember, esomeprazole is a pure E isomer, whereas the omeprazole is a racemic mixture. The major, in fact, before we look at the major, let us look, I believe it is somewhere drawn. Just wanted us to look at the enzymes. No, I thought I have them somewhere. Where is this? Yeah, here we are. So this is oxidation sites and cytochrome P450 isoenzyme, the metabolism. This is omeprazole. That's a methyl group, methoxy group, and so on. So we are looking at the enzymes that are responsible for the metabolism of omeprazole, and you can see we have this methyl group. This methyl group here, that's on the side of the of the pyridyl nitrogen. This methyl group can undergo oxidative hydroxylation to the alcohol and then to the carboxylic group. We have done that a lot, and that is catalyzed by cytochrome 2C19. So cytochrome 2C19 catalyzes the oxidation of that methyl group. This sulfoxide can undergo further sulfoxidation to the sulfone. Now it's a sulfoxide. It can undergo further sulfoxidation to the sulfone. So it's oxidized to the sulfone. The main enzyme there is cytochrome 3A4. Then this methoxy group here can undergo oxidative O demethylation. Oxidative O demethylation, again catalyzed by cytochrome 2C19. So that is how omeprazole is metabolized. So when we look at esomeprazole, it is just the differences in the activity of those enzymes that brings about the change in the reactivity of esomeprazole compared to omeprazole. So let us now go back. I just wanted us to note that, and as we note that, then we are able to now understand the major inactivating metabolic reactions of omeprazole include benzylic hydroxylation, that is that Ben-methyl group, catalyzed at carbon 5, catalyzed by cytochrome 2C19, sulfoxidation to the sulfone, catalyzed by 3A4, and non-enzymatic reduction of the thiol ether. And also, we have also said, so there can be non-enzymatic reduction of the thiol ether, but there is also oxidative or demethylation of the methoxy group on the benzimidazole. The sulfoxidation is inhibited by concomitant consumption of grapefruit juice. So in other words, grapefruit juice can inhibit the metabolism of omeprazole, of course, leading to drug interactions. As omeprazole is metabolized at a much slower rate and has a higher dependence. So that you see that's now the advantage. As omeprazole is metabolized at a much slower rate and has a higher dependence on cytochrome 3A4, which can conduct some of the cytochrome 2C19 catalyzed reaction, but does so at a less vigorous pace. So the reason why the esomeprazole has higher activity is the fact that it is more slowly metabolized, and therefore you maintain very high concentrations that are needed for the better activity. Omeprazole and esomeprazole both inhibit the cytochrome 2C19, thus inhibiting their own metabolism with chronic dosing. And that's what we are saying. Omeprazole is a substrate primarily of the cytochrome 2C19 and may elevate concentrations of other substrates for these enzymes. In other words, omeprazole, you can also have quite a lot of drug interactions where you have drugs that are metabolized by the same enzyme. They'll compete for the same enzyme. For example, the benzodiazepam can bring about a drug interaction. This is because both of them are substrate for the cytochrome 2C19, because the main metabolizing enzyme for omeprazole is cytochrome 2C19. So once that enzyme is inhibited, or if there is competitive inhibition, then you can also get toxicity. Since esomeprazole is metabolized at a much slower rate than the racemic omeprazole, it has a slower clearance in a higher area under the curve. There is a lower risk of interpatient variation as a result of the cytochrome 2C19 phenotype, and it has a faster onset of action compared to omeprazole. There is a lower risk because we are saying the esomeprazole is not wholly metabolized by cytochrome 2C19. It's also metabolized by quite a lot by the cytochrome 3A4. So even if somebody has interpatient variation, in other words, they have alleles of cytochrome 2C19, you will not get a lot of toxicity because there's an alternative metabolism of esomeprazole, and also the rate of metabolism by the cytochrome 2C19 is already reduced. So that also hinders you to have a lot of toxicity with esomeprazole. Salt formation, the sulfoxide group is highly electron withdrawing group, also weakens the normally neutral pyro NH bond to the extent that it can actually be lost when treated with magnesium hydroxide. As a salt, esomeprazole magnesium can be dissolved in water for short-term IV administration when oral therapy is either not feasible or inappropriate. All we are saying, you see that sulfoxide group highly electron withdrawing. It weakens the NH, normally the neutral pyro NH bond, to the extent, so that now if you lose the H, if you lose this as a proton, then you can form N magnesium. So you can form, if you lose this as a proton, the proton, in other words, can be replaced with a magnesium by loss of that proton. So we are only saying, if you look at the structure again, not for all of them, but for some of them, you can form the salts. So we are saying this is highly electron withdrawing. This sulfoxide group, and we say that electron withdrawal helps in creating an electrophilic carbon here. If this carbon is highly electrophilic, it will also pull electrons from here, and of course remember the nitrogen, so making this nitrogen a little bit positive, the nitrogen then becomes electrophilic, it pulls electrons strongly, and therefore this hydrogen can be an acidic hydrogen. This is a hydrogen, we are talking about that hydrogen being this hydrogen being an acidic hydrogen, and if it becomes an acidic hydrogen, that is why we are saying you can react with magnesium hydroxide and you form magnesium esomeprazole, and you can use the magnesium. Remember, when you form salts, you form salts for purpose of increasing water solubility, for usually more often than not for parenteral administration. So that's all we are saying, that you can form magnesium esomeprazole, and once you have formed the magnesium esomeprazole, you can use it. You can use it parenterally. You can use it parenterally. I think most of that slide we have done. I keep touching the wrong button. Slide we have already looked at it. Salt formation, we have just said you can form the salt formulation for parenteral administration, and therefore we do have esomeprazole magnesium. For some of these drugs, the problem is that they are quite expensive. So that is one of the drugs. The other one is lansoprazole. If you look at lansoprazole, again, I hope you have the structure somewhere near. You will see it said it has a trifluoroethoxy ether. It has a trifluoroethoxy ether, and therefore we are saying, if you look at the trifluoro is CF3. That is electron withdrawing, but because of the oxygen and then the ethoxy group. You see, this ethoxy group gives us some distance between the trifluoro group and the pyridyl ring. There is quite some distance, and therefore, although the trifluoro group is electron withdrawing, the ethoxy group allows for electron donation, and therefore that group still donates electrons into the system rather than withdrawing, although it has a trifluoro group. Of course, the trifluoro group will improve in lipid solubility because halogens do improve in lipid solubility. So despite the negative inductive electronic pull of the 3 fluorine atoms of the trifluoroethoxy ether at carbon 4 of the pyridine ring, the ether oxygen can still donate electrons through the pi system to increase the nucleophilic character of the pyridine nitrogen and therefore anionize. So if you look at that long substituent on lansoprazole, we are still saying, yes, it has a trifluoro group. We know a trifluoro group is electron withdrawing, but we also have the ethoxy ether. There is the CH2 oxygen, and that ethoxy ether or that ethoxy oxygen can still donate electrons through resonance, and therefore that group is still an electron donor, and therefore still making the pyridine nitrogen more nucleophilic, and therefore more readily attacking the electrophilic carbon. A single methyl group assists in this effort by pushing electrons towards again, we had mentioned methyl groups push electrons through positive inductive effect. So those are the two roles. Those are the explanations of the groups that we have there. There is no electron donating carbon-5 substituent of the benzimidazole ring to augment the electrophilic character of carbon-2. The rate of formation of the reactive sulfonamide and sulfonic acid intermediates is still relatively fast for lansoprazole. So the two groups, although we do not have any group in the benzimidazole group, we have two substituents on the pyridyl group, allowing again for rapid formation of the sulfonic acid or the sulfonamide, and hence enhancing the reactivity of this molecule. And lansoprazole is metabolized predominantly again by cytochrome 2C19, but its reliance on the enzyme is somewhat less than that of meprazole. Meprazole is one of the drugs that heavily relies on the cytochrome 2C19, and that's why we said there can't even be what we call polymorphism. There can be polymorphism, and we did in fact also we talked about drug interaction because of its high reliance on cytochrome 2C19, because cytochrome 2C19 also metabolizes many other drugs. Along with omeprazole, it is claimed to both competitively inhibit cytochrome 2C19 and induce the synthesis of cytochrome 1A isoforms, but there are no clinically significant drug-drug interactions reported in the literature for lansoprazole. So it's a little bit safer than omeprazole, but it also will inhibit cytochrome 2C19, but because it's not being metabolized mainly by cytochrome 2C19, although it will inhibit the same drug, the fact that it is not predominantly metabolized by cytochrome 2C19, that is why we do not have very many drug-drug interactions. So that is lansoprazole. Then we have pantoprazole. If you look at pantoprazole, we said pantoprazole, I think, is one of the drugs that has, on the benzimidazole ring. The benzimidazole ring, it has a, I think, it has a difluoromethoxy group. Difluoromethoxy group. Let us look at that drug because that drug is quite a lot of interest. Pantoprazole. It's pantoprazole. This is a pantoprazole, yes. This, you can see this trifluoromethoxy group, as we had mentioned, trifluoromethoxy group. And this trifluoromethoxy group, see, this is not this, if you look at, you can pair this with the trifluoroethoxy group found in lansoprazole. So this is where we were. There was this separating group here. It's a bit different because of this separation of this group here, the oxygen is still able to donate through resonance. But unfortunately here, because the oxygen is directly attached to the trifluoro group, this trifluoro group withdraws electrons, and therefore the net effect in pantoprazole is a bit of electron withdrawal, and that explains why, when we looked at the pantoprazole, we did mention that it's pKa2. It has the lowest pKa2, and therefore a high Ka. It has the lowest pKa2 and therefore a high Ka2, and hence it has a lower. It's one of the. It is the least. It's the least potent. It is the least potent of the PPIs, as I have said. It's because that group does. Because of the fact that the trifluoro group is very close. Trifluoro group is very, very close to the oxygen, then you find that group can withdraw electrons rather than donate electrons. Electron withdrawing difluoromethoxy has replaced the carbon 5' methoxy group found on the benzimidazole moiety of omeprazole. The difluoromethoxy group, along with the electron withdrawing sulfonyl group, makes the normal and neutral imidazole NH group acidic enough for water-soluble sodium salts. So that is an advantage. We are saying this difluoromethoxy group, rather than being an electron donor like the methoxy group found in omeprazole, it's more or less an electron withdrawing group, because as I have said, the oxygen is too close to the electron, very, very powerful electron withdrawer, the trifluoromethane group. These two fluorine atoms are also close enough to the oxygen atom to impact its electronic character, despite the fact that the 4-methoxy group on the pyridine ring is trying to enhance the anionized pyridine nitrogen nucleophilic character. The 5-trifluoromethoxy group on the benzimidazole has a decidedly inhibitory effect on the ability of the benzimidazole N3 to protonate. All we are saying is that the difluoromethoxy group on the benzimidazole ring, I don't know why they put it. I think when they are developing these drugs, whenever they get a drug with a perishable activity, of course they market it as they continue looking for other drugs. So the difluoromethoxy group in pantoprazole, we are saying, because of the closeness of the oxygen to the trifluoromethane group, then that group is more of an electron withdrawer than electron donor. Increasing the nucleophilicity of the benzimidazole N3 nitrogen, it will decrease its nucleophilicity, and therefore it will actually decrease its pKa, and therefore decrease its basicity. In decreasing its basicity, it will decrease its tendency to protonate, and therefore that is the reason which we can use to explain the low reactivity of pantoprazole compared to omeprazole, compared to lansoprazole. Because pantoprazole at the benzimidazole position 5', it has a group that is predominantly an electron withdrawer. And because it's an electron withdrawer, it reduces the ability of the benzimidazole pi nitrogen to protonate, and therefore will decrease the ability of that nitrogen to withdraw electrons from the 2' carbon, making it highly electrophilic, and therefore it reduces the ability of the pyridine nitrogen to attack the carbon, to the electrophilic carbon 2', and hence reducing the activation of pantoprazole to the sulfenamide, first of all to the speed-up intermediate, and then to the sulfenic acid, and finally to the sulfenamide, and hence you reduce its ability to form the drug ATPase enzyme adduct, and that explains the lower reactivity of pantoprazole. So that is all that slide is saying. Pantoprazole has the lowest pKa, and you know, the lower the pKa, the higher the Ka, the lower the basicity. This means that the benzimidazole N3 is more reluctant to take on a proton compared to the other PPI structures which have a pKa which is much lower, much higher. Since the benzimidazole N3 protonation step is essential for the activation of carbon 2' for nucleophilic attack, the overall reactivity of pantoprazole is the lowest of all the PPIs. That is the same thing I've explained. The half-life of pantoprazole at pH 30 is a whooping 9.3 minutes, documenting a much slower conversion to the reactive sulfenic. You might not require to remember the minutes, but we are only saying that it has lower reactivity compared to the other PPIs, and that can be explained by the group it has at position number 5'. The much slower activation of pantoprazole compared to the other PPIs means it has time to react and inactivate other cytochrome, other cysteine, other sulfhydro-containing groups or sulfhydro-containing molecules, and therefore it has lower selectivity. All we are saying, because it will stay, when you give pantoprazole, its rate of activation is much slower. It gives it time to react. It reduces its selectivity, and therefore it can react with other. It's present. It's available for a longer period, and therefore it has time to react with other sulfhydro-containing receptors, and therefore reduces its selectivity. That is selectivity observed. The omeprazole has been lost, so it reduces its selectivity, and therefore it could have more toxicity when compared to lansoprazole and omeprazole, and also esomeprazole. The cytochrome 2C19 pathway is most critical for pantoprazole inactivation, although cytochrome 3A4 is also involved. No clinically relevant cytochrome-mediated drug-drug interactions have been noted with co-administration. So the only drug which has been found to have drug-drug interactions is actually omeprazole. We did mention esomeprazole. We have reduced because we are saying its rate of metabolism by the cytochrome 2C19 is much reduced compared to the rate of metabolism of omeprazole, and therefore reduction in drug-drug interaction. And no wonder esomeprazole is a much better drug than omeprazole just by change of the stereochemistry. Okay, the last one, labeprazole. This PPI is the most highly reactive of those currently marketed. It will have the highest pKa1, the highest of any available, and we have now said when it has a very high pKa1, we understand now what happens. The high parietal cell concentration of labeprazole compared to this other PPI is certainly one factor in superior anti-secretory activity. Once it has a high pKa1, it will be protonated very quickly, and therefore you will retain very high concentrations within parietal cells. Also, the concentration of the pyridyl non-protonated will be high. It also has a high nucleophilicity, high attack, and that will explain the reason. So one of what we are saying is that once it has a the high pKa, it will be protonated very rapidly. The minute it gets in, it's protonated. Once it's protonated very quickly, it prevents any of the drug from the back diffusion, moving back out of the cell. So there will be very high concentration within the parietal cell. It has high nucleophilicity, high rate of attack, and all those things that we have mentioned. And therefore, it definitely has the highest reactivity. The relatively high pKa, also the high parietal cell concentration of labeprazole compared to the other PPIs is certainly one factor in the superior anti-secretory activity. It also has a high pKa1, indicates that the nucleophilic characteristics, all these we have mentioned, just are going round and round. So once you understand the pKa1, pKa2 for all the other drugs, you will be able to explain also for any drug that you are given. All we are saying is that the higher the pKa1, the better. The higher the reactivity, the higher the rate of reaction, and therefore the more potent that drug will be. The high pKa1 is attributed to the electron donating effect of the methoxypropoxy substituent. The methoxypropoxy substituent, if you look at it, it has a very long, if you look at its group, it does not have any halogen like the others. The other have halogen, so this one does not have a halogen. It is also very lengthy, and therefore the methoxypropoxy on the pyridine ring, which provides a great amount of pi electron push than the trifluoro. You see, this one already has a fluorine that reduces the electron of the availability of the electrons. So this group, the methoxypropoxy substituent, is good enough. It's conducive enough to give very high concentration of electrons compared, of course, to the trifluoro, whereby you have a slight negative inductive effect. Even though there is a lower percentage of the pyridine nitrogen in an ionized form, this is overcome by the fact that the pyridine atoms, which are ionized, are highly basic and ready for the intramolecular nucleophilic attack of the benzimidas or carbon-2 position. All we are saying this point is saying, of course, when you have very high nucleophilicity, of the pyridine nitrogen, then most of the pyridine nitrogens will be protonated. It's a stronger base. If you have a drug which has a stronger base, it is more basic, and therefore it is more basic. Therefore, most of it will be in the ionized form. You will have very little of it in the anionized form. But we are saying the little that you have as the anionized form, that is the pyridine is anionized, has very high nucleophilicity. So that the little you have will attack the carbon-2 prime very quickly. And remember, we said the minute you remove any of the non-ionized pyridine to attack or in the formation of the spiro intermediate, then more of the anionized pyridine will be produced, because you must always maintain your equilibrium. So we are saying, yes, there can be a negative effect of that nitrogen being highly nucleophilic or being highly basic, because the more it is basic, the more protonated it is. Yet we require the non-protonated pyridine for attack. So but we are saying the advantage is the little you have of the non-ionized pyridine has high nucleophilicity. So immediately that little you have will attack. Even if you have 2 molecules, they will attack the electrophilic carbon 2 prime, and the minute they attack, you get more generated, attacking very fast. So that will still push the reaction to completion. So the fact that this drug is more basic does not render it less potent, or does not render it less potent in not being able to attack the carbon 2 prime, because we are saying, because the nucleophilicity allows it to attack the carbon 2 prime much more quickly than its reactivity is maintained. So please do understand that explanation, that of course you will have more ionized, more of the ionized dication, the pyridine ionized, the benzimidazole ionized. But the fact that whatever little of the anionized is available has high nucleophilicity, there will not be much effect. There will be not much. There will not be much influence on the attack. In fact, there will be positive influence on the attack of the carbon 2 prime, because it will be attacked very readily, and therefore the reactivity of rabeprazole is to maintained to be the highest. In addition, the pKa2 value of this is 0.62, provides a level of benzimidazole N3 protonation. In other words, it also has a high pKa2 compared to the others, like I think like pantoprazole, I think we saw it was 0.11. So it still has it also has a high pKa2, it has a high pKa, allowing for the protonation. Once it's protonated, again, remember, once the benzimidazole is protonated, it will pull away electrons, make the carbon 2 prime more electrophilic, and again allow for the activation. Remember, we require activation of this drug, and without activation, these drugs will not have any activity. So that explains, those other slides are just explaining what I have just explained. All we are saying is that when used in combination with amoxicillin and a clarithromycin for the eradication of H. pylori, rabeprazole produces positive results in 7 days compared to the 10 to 14-day course of therapy recommended for esomeprazole and lansoprazole, respectively. So all we are saying is, because of the structure, the reactivity of rabeprazole is because of the structure. And we have what we call the combi pack. Of course, when you do your pharmacology, you do much more of that. So it has been found that when you combine amoxicillin and clarithromycin in a combi pack, and you're giving this together, of course, with either the esomeprazole or with rabeprazole as your anti-ulcer drug, then you can get eradication of the H. pylori, because H. pylori is one of the microorganisms that is found to be very difficult to manage in ulcers. So you give very aggressive therapy. You can see that's clarithromycin in combination with amoxicillin, that very, very, very aggressive therapy, and of course with either rabeprazole. But we are saying with rabeprazole, you will give 7 days, and with either esomeprazole or lansoprazole, you will give 10 to 14 days. So you can see the advantage of the higher reactivity of the higher reactivity of rabeprazole. That higher reactivity gives advantage. But of course, the higher the reactivity is, the more modern the drug is, the more expensive it is. That is the only problem. That drug will be unaffordable, to be unavailable for many because of the cost implications.